All right, it's 10 o'clock, so I think we'll make a start. I'd like to start by welcoming you all. I see that we have quite a full room today, so we're very glad to see that everybody's joining us for this very interesting webinar we've got in store for you. Let me start by saying a big welcome to everybody to this webinar on life cycle assessments for the automotive sector. We are today co-organized by the ALMA and FLAMINGo projects. My name is Jose Uribe. I'm from the International Solid Waste Association. We do the communications and disseminations for the ALMA project. Our co-host for today is Dr. Ioanna Katsavou from Excelsis, who do the communications and disseminations for the FLAMINGo project. I'm very proud to say that we have the support and participation today also of the Enlight EV cluster, which includes, of course, our two projects, ALMA and FLAMINGo, and also the projects Revolution, LEVIS, and Fatigue for Light. Today, we are also joined by the SALEMA project. All of these projects are receiving funding from the European Commission through the H2020 Innovation and Research Program. So thank you to our sponsors for that. And one of the things that I'd like to start, of course, explaining is what is the Enlight EV cluster. This is a group of like-minded projects that are focused on what we call lightweighting, which is the concept of trying to reduce the weight of vehicles. This is, of course, a strategy that is useful for reducing the energy consumed during the use of the car. And of course, we do this trying to find either lighter materials that we can use or optimizing the design of the parts, and perhaps also including new materials. So we hope that by lowering the energy consumption during the use, we can also extend the range of the vehicles, for example. And one of the important things, of course, that is another advantage of what we're trying to do with lightweighting is we see that with electric vehicles and as our power grid shifts from fossils to renewables, the largest relative contribution of the use of the energy, of the emissions coming from the use of the car come to the production of the car. And we have a little bit of a problem with either echo or an open mic. So if you could please all close up your mics, that would be useful. Thank you. As I was saying, we want to lower the emissions, and we need to make sure that we don't just focus on the actual use of the car, because when we are all driving electric and the electricity all comes from renewable sources, then of course we have very low emissions coming from the use. So we also need to make sure that for the long-term viability or sustainability of vehicles, we need to focus also on the production side. And at this stage, of course, then we say, well, lightweighting with less mass, this can have a positive impact on sustainability. And in principle, it can also reduce the amount of resources necessary when we're trying to produce the car. And you'll notice that I hedge there a little bit with can have a positive effect and in principle. So the main reason I'm doing this, of course, is because we don't know this until we measure it. As an engineer, one of the first things I was taught was that measuring is knowing. And therefore, if we can see what it is that the effects are of our design decisions, then we can see whether the trade-offs are worth it. Because, for example, what if the energy required for the new production of the new materials exceeds the actual savings during the use or manufacture? This is, of course, where the LCA comes in. The LCAs allows us to measure or to know which trade-offs serve the ultimate goal of sustainability and which do not. One of the things that I stumbled upon while trying to research some of this is, of course, a saying that says, if you can measure it, you can improve it. And this is an important factor, I think, also for LCA, because the LCA is not just a way of maybe proving or trying to ensure that our current design decisions are the proper ones, or that they have the proper trade-offs, but also it can allow us to analyze where most of the emissions or the problems for sustainability are coming from, which means that then we can also look more carefully at where do we put our innovation and research efforts into so that they can have the largest payoff when we do resolve the issues that we encounter. This is, of course, very important when it comes to making sure that overall we achieve sustainability. And for this, of course, we also need to know that our LCA approaches and our LCA systems that we develop are correct and reliable. LCA is a rather complex topic, so I will not talk too much about that. That is why we have today all of our experts who will be talking about how they approached this complicated and difficult subject, the assumptions that they might have made, and this data that they might have used, and how that all compares to other approaches from other projects, so that we can all exchange some knowledge, maybe best practices, and see how we can bring forward the science of LCA assessments forward. So I'm running out of time for the introduction here, so I will hand you over to Dr. Ioanna Katsavou from Excelsis, who I think will tell you a little bit about the housekeeping rules for today and introduce the first speakers. Thank you and welcome all.
Thank you, Jose. Welcome all. Good morning from me as well. As Jose mentioned, I'm Ioanna Katsavou from Excelsis, a Greek consulting company. I'm a chemical engineer and the dissemination manager of the FLAMINGo project. FLAMINGo is, of course, a Horizon 2020 project that is aiming to the development of lightweight aluminium metal matrix nanocomposites and their validation in green vehicles. Let me start, of course, by saying that I'm very happy to be part of the organizational team of this workshop, as sustainability in the automotive industry, which is, of course, a very energy-intensive sector, is highly important. So LCA assessments and approaches are very crucial and so much needed. Before we start with the presentations, I would like to highlight some organizational aspects. So please make sure to keep track of time, as we would like to follow the agenda. We can take questions, always depending on time, either right after each presentation, or I would like to highlight that we have a slot for open discussions as the last item on the agenda. Questions can be asked through the chat, and then me and Jose will collect them and will direct them to the presenters. So please use your name, position, and the presentation or the presenter that you are addressing the question to. And lastly, I would like to let you know that this session is being recorded and it will be available on YouTube after this webinar. So I do not want to delay anymore the workshop, and I would like to give the floor to the first presenter, which is Mrs. Raquel Ledo from the Automotive Technology Center of Galicia.
Hello.
Raquel,
hello, can you hear me?
Yes, very well.
Perfect, thank you. I'm going to share my presentation. Sorry, because I have two screens and you can see my screen now?
Yes.
Yes? Okay. So please, if you detect some problem with the sound or something, let me know, okay?
Yes.
Okay, perfect. So thank you very much. Thank you, Ioanna. Thank you, Jose, for the organization and for this introduction. My name is Raquel Ledo. I am the responsible for materials innovation area at CTAG, Automotive Technology Center of Galicia. And today I could introduce ALMA. ALMA is a collaborative, ALMA is a collaborative project funded by the European Commission under Horizon 2020 program, and specifically related to the topic advanced light materials and processes for automotive applications. So some general figures. We are 9 partners from 4 European countries, including 5 industrial companies, 3 RTOs, and 1 international association. Our budget is around 4 million euros, and the duration of the project is 3 years. So we have started in February 2021, so we have just entering in the last year of the project. Our main goal is obviously the lightweighting, but we have identified these specific objectives that you can see in my screen now. We can summary in these key points. We need to lightweight, it's clear, but we can't forget the safety of passengers. This is a must. So the material performance should be the highest possible. It's clear that we have to lightweight, but we have to meet all the requirements in the car. We want to decrease the global environmental impact, so we have to apply eco-design strategies to enable effective recycling, recovery, and reuse at the end of life. We want also to promote the sustainability at the circular economy, and it's clear we are in the automotive sector, so all these solutions should be affordable. As I mentioned before, we are 9 partners composed by 5 industries, some big ones as Ford or ArcelorMittal or BAT, some SMEs, is the case of Rescol and Innerspec, 3 RTOs, CTAG, Fraunhofer, ITWM, and TNO, and 1 international association, ISWA. This picture represents the ALMA concept, the ALMA approach, but we would like to go in detail, not a big detail because we have no time, but I'm trying to summarize the work we have carried out until now. First of one, we have the first step was to adapt the structure of a ICE model, an internal combustion engine model, to a BEV model, a battery electric vehicle model. So this was the first step. When we had the first version of this electric model, we start the optimization of design. So there are several key points that we have mentioned here. The first one is that we have to choose the best material for the best location. This is really important because sometimes the materials are really high performant, but we are not putting in the good way. So it seems that it's something very simple, but it's not the case. So it's really important to choose the best material for the best location. The fact of using new high-performance materials allow us to integrate functions. That means that in some cases, at the first point, we had 2, 3, 4, or 5 different components, and now we are able to integrate in one only component. And this is thanks to the typology of the materials, but also thanks to the redesign of these parts. And the last point is really important, that when we are designing this new structure, we are not only thinking to meet the requirement for the function of the car or for the life of the car. We are also thinking what is the solution for the end of the life. So when we are designing, we are thinking in the use, but also thinking in the future. So the main partners involved in these steps of redesign the structure and design BEVSIM tool that I talked before was CTAG and TNO. Then we pass to the point of the innovative materials. In this case, the 2 main partners was ArcelorMittal and BAT. In the case of ArcelorMittal, they have developed high-performance new steels. we are using these new steels in 165 parts in this new body in white of ALMA project. Something, and in some cases we are able to, as I mentioned before, to integrate functions. Is the case of the edge frame or the door panels. So we are able to integrate 2-3 components in one only component. And we are using also the structural MEC sheet molding compounds, in this case developed by Batch. And in the cases, the usage cases we have select for this is the battery cover and the dash panel. So we have a new design, we have new materials. So our partners, Fraunhofer and Ford, entered in action to develop and to characterize, firstly, these new materials. Fraunhofer has developed the new material cards and compiled all the information and all the required characterization for these new materials. And our colleagues from Ford has carried out all the validation, all the virtual validation, to be sure that this new design with these new materials meet all the requirements in terms of crash, front crash, back crash, lateral crash, etc. It's clear that at the beginning we find some problem and we have to redesign, but now the results are really good. So we have the design, we have the materials, but we have also parallel technologies, we can say. Is the case of this, the bondable adhesive. In this case, is thinking in the end of the life. So we are going to use this adhesive to join the hybrid components, that is one component from steel and other component from SMC. And the idea is that at the end of the life, by applying high temperature is around 250 degrees, 50 degrees, more or less, we will be able to separate, to disassembly in an easy way. And the other innovative technology is concerning the health monitoring. Our colleagues in SPEC are developing a technology based on ultrasounds that is able to determine the condition of the part. So we will be able to determine if this part could be reused, or we have to recycle, or we can choose what is the function at the end of life. So this is in general all the approach we have in ALMA project. At this point, with the work we have carried out until now, we can say two main results. One is the BEVSIM tool that my colleague Tom will explain in detail. I think it's really a very useful tool that can help the designers to take into account the LCA and LCC parameters to have a better design of the part. But Tom will explain in 5 minutes. And I think I pass. Yes, in this point is the other good point is that we all work carry out. We have reached a lightweighting potential, a potential lightweighting of 23% of lightweighting concerning the baseline. So we are really happy of this at this point. We think that the potential impact we can have in the future vehicles is really important. So now in this last year of the project, we are we are focusing in the manufacturing processes. That means that we are going to develop some demonstrator parts in steel and in SMC to check the results we have obtained in the virtual validation, and to check the feasibility of the parts with these new materials. But we are really confident that this point is really good and with a high potential for the new vehicles. So from my part is all a brief introduction to ALMA. I really want to thank to all consortium, all partners involved in Light consortium, because I think the fact of sharing results between different consortiums and from different projects is really important. This webinar is one sample for this. We have developed some activities during this last year, and we will have more joint activities in the future. And if you want to know more about ALMA, please don't hesitate to contact by social network, by our web page or something else. So thank you very much. I think I have respected my time, my slot, and it's all. Thank you.
Thank you, Raquel. I think that we can pass to the next presentation, and then we can have all together questions maybe for this part, as it refers to the ALMA project. Is this okay with you, Raquel?
Yes. Mm-hmm.
Great, great. So I would like to invite Mr. Tom Ligthart from TNO to present the BEVSIM tool.
Yeah, and thanks, Raquel, for already introducing it. So let's see. Is my presentation visible now? I think so.
Yes, it is.
Yeah, okay. Yeah, the BEVSIM tool, it's the result of a team of TNO, and of course also input by the partners to fill the database. I will be presenting it today. I'm Tom Ligthart, senior scientist from TNO, an RTE from the Netherlands. And I'm going to show you some things on the BEVSIM tool. So first a short introduction, and let's see what the capabilities of the tools are, and first kind of simulation of the workflow. And after showing the results, I'll end with some closing remarks. BEVSIM, it looks over the full life cycle of a battery electric vehicle, and BEVSIM stands for Battery Electric Vehicle Sustainability Impact Assessment Model. It's an LCA model, so you can really do an LCA with this tool, as all the materials needed for the production of a car, the processing of the materials into parts and choices to be made for the use phase, the end-of-life fate, and the end-of-life recycling processes can be made, and we are aiming at the segment C and D passenger cars. It can be customized BEVSIM, so you can model a full car or include or focus on a subsystem like the body and weight, or even go to designing a part and comparing that with reference parts, for instance. There is also the possibility that the customer includes its own specific data sets. The results, you can download these as a Word report, but also in an Excel workbook. And of course, the benefit of an online tool is that we have the version control, and that we can easily update the lifecycle inventory data sets, but also the methods included in BEVSIM. And so with this tool, you are able to do the full LCA, and so really have a fast result, and also people not specialized in LCA can do this. It's designed for the non-LCA experts, like the designers of parts, materials, and complete vehicles. The capabilities of BEVSIM, it has let's take a pointer. It of course has an LCA part, but also life cycle costing, LCC, and a circularity assessment. And later on, with Ximena, of Global Factor, I will present something about circularity in the automotive industry. So you can see what is the impact of the lightweighting, the measures that you take, and see what are the effects of material choice, but also, for instance, the use phase. In which country are you taking your electricity from for charging your car, and are you using gray or green electricity? Also, future recycling scenarios have been included in the end of life, so you can also look at the future end of life performance. Then all the life cycles phases are included, so the raw materials, yeah, all the things you need to make a car, and also the processes to make parts of these materials. And plastics is included with compounding, injection molding, and also, of course, metals with the stamping, casting, all kinds of processes, and also the painting and the assembly of the car. As said, in the use phase, you can look at the energy consumption of the car, and it depends, among others, of the weight of the vehicle, and that's automatically included already, but also maintenance is included, and changing of parts during the life cycle. In the end of life, the current scenario is there, but also a future scenario. Recycling, but also energy recovery that avoids the production of materials and energy. That is also part of this tool. Yeah, you start with BEVSIM by first selecting a user design. There are already some there, and yeah, you can then select it, and further on can edit this this user design. But you can also do it at the subsystem level, for instance, body in white, or even a part level. I said also LCC is part of the tool. There is a database in it with default material costs. Also, user costs are included, so that's the consumer. And you can edit these prices to suit your own needs. And then in the user design, well, as said, you can select the type of electricity or fuel in case it's an internal combustion engine, select consumer price, and other cost elements. That's then all used in both the LCA and the life cycle costing. Then, oh, this was going too quick. You can edit the user design that you've chosen. You can save it under another name. You can add or delete parts, and also with those parts, you can select the materials, change it. You can select up to 3 different processes to model the material into a part, and also their efficiencies are taken into account. So, well, you only have to give the amount of material in the actual part, and the tool will calculate the final material needs. And it also accounts for the recycling, treatment of the production waste, but also the end-of-life waste. That's all included. Then you select up to 2 different reference designs with which you then can compare your own user design. And well, you then select the use phase method. For instance, which country do I take my electricity for the consumer from? Is it gray or is it green electricity, as that will affect the performance in the use phase. The end-of-life scenarios are then selected. There is a current reference scenario, but you can also have future scenarios in which we have chemical recycling for the plastics and the sheet molding compounds, because they can become more and more important, of course, in the automotive industry. Yeah, here is just a selection, a comparison of two different designs, battery electric vehicle and the internal combustion petrol car. Yeah, what you do in this case, well, body is the same weight. The chassis of the battery electric vehicle is heavier, and of course also in the powertrain, because the battery is there is a higher mass. But indeed, so lightweighting of these electric vehicles is of importance. Then you can evaluate the sustainability impacts. You have a spider graph comparing your up to 3 different cars in the spider. With, in this case, we show the impact categories of recipe, a much used environmental impact assessment method. But what you can also do is that you go to a bar chart. To a bar chart, and then, for instance, if you're looking at the parts level, you can also have a look at the subsystems or materials, but here an example of the parts level is shown, and then you see what is in the materials, what is in the assembly, end of life, etc. That's all shown. And so that's also a way to look at it and see where my hotspot, my most important impacts are. Then for the life cycle costing, we have two perspectives, that of the consumer. So the price that the consumer has to pay for the vehicle, but also the other costs like taxes and energy cost. And in the end, you might have, for the end-of-life vehicle, there might be some revenues. So that's included. Also the producer's perspective, and there you see material costs, processing costs, but also costs that have to do with, for instance, callback actions, and of course the revenues. That's also a possibility to do. And this is then for the consumer. Of course, the purchase costs are the most important ones, but these are costs from the use phase, and that may be taxes, but also energy costs, and there can be some small revenues at the end of life. And then you see the total life cycle costs for the consumer. So that's also a thing which you can take into account. For the producer, that's again, things like the manufacturing costs and other costs, and of course the revenues that come from the sales. Some closing remarks. So it's BEVSIM. It's an online tool with which you can assess the environmental impact via LCA. You can assess the circularity, show it more on that later, and also the impact, economic impacts. Also have the consumer perspective, which might be a kind of sales argument if you have a better performance there, for instance, in the use phase. It's specifically designed for non-LCA experts in the automotive sector. And as said, you can model a whole vehicle, but also parts. And the tool gives consistency above, over all the LCA studies that you do. BEVSIM is also accessible for third parties, and we can have a discussion for that on a case-to-case basis, and that can also be a modification of BEVSIM. Then, so this is the end of my presentation. I'll present you the ALMA team. Originally, Rajesh Mehta, but he had to leave TNO, was the work package leader for this. Now I am the leader, and these are the other people that contributed to the filling and designing, constructing the BEVSIM tool, and also to get it as an online tool available for others. As said, we were funded by the Horizon 2020 project, and we had input from our partners in the ALMA project. So, as already said, it's also an introduction is also available on YouTube, and of course you can contact me for further details. That's my presentation. So I don't know whether there are questions.
Thank you, Tom, very much. Indeed, there are questions for both you and Raquel. So I will start with a question for Raquel, since we have some time. It is from Ignacio Zurano from Lomartov to Raquel. Congratulations for the presentation, and he would like to know more about the energy consumption that this process that you're developing has, comparing with the baseline.
Yes, I have just answered by the chat, but I repeat, it's very simple. If we talk about the energy consumption for the global vehicle, for the functioning of the vehicle, we talk about 6% more or less of energy reduction. But we also can talk about energy consumption in terms of manufacturing processes. I talked before that the new high-performance steels allow us to reduce the thickness of the parts. So the energy we need for manufacturing these parts is lower. The fact of being able to integrate functions allow us that instead to manufacture 2, 3, 4 different parts with 2, 3, 4 different tooling, now we are joining in only one, so we are also reducing. But it's true that at the moment we have not quantified this reduction. But we have the two ways: the global energy consumption, 6% more or less, and this other that I have not a number just now.
Excellent, thanks.
Thank you.
Thank you, Raquel. So the next question is for Tom. It's from Maria Welmius Henriksson from Volvo Buses, and they're asking, could BEVSIM tool be used for heavy-duty vehicles, even if it is designed for passenger cars?
Yeah, that's in principle, that's possible, of course. You will have to further define the parts of that vehicles, and in case other materials or processes are being used, these also have to be included. But that's all possible to customize BEVSIM for a specific use. And what you could also think of that manufacturers of the original equipment, they want to focus on parts, also need more specific materials. That's also a possibility in BEVSIM.
Thank you, Tom. So one more question for you from Carla Barbati from Constellium. The question is in the part of the processing of metals, is the extrusion process included in the BEVSIM tool? And also if which metals or alloys are included? Is it aluminium alloy included?
Yeah, aluminium is there, and of course also processes like the extrusion. So for each material, there is a set of for material specific processes. So once you have selected a material and you then want to go to the processes, you only see the processes relevant for that kind of material, and there are different types of steel in the BEVSIM tool. And also for sheet molding compounds, we have 2 different types that are being developed in the ALMA products. These are also included in BEVSIM. And perhaps coming back on the question on the energy consumption, we have the cumulative energy demand as an impact assessment method in BEVSIM. So you can also see what is the cumulative energy demand related to materials, processing, use phase, etc.
Thank you. Great, Tom. So we have some time for some more questions, so we'll proceed. The next question is regarding the functionalities for inputting real-time production data. Are you planning to include such functionalities in the tool?
Yeah, real-time production data can be included in the database, so not really real-time, but once you have data that you collected in real-time, that can be included in the tool, and so that can also be kind of overall processes that are there for the whole car.
Okay, great. And as we are all familiar with the LCA software like Sigma Pro, what is the difference using this tool compared to the traditional ones?
Yeah, so this is really a tool that is, as the main audience, see designers that are not familiar with LCA software. And as I showed, you can edit a design that's already there, change a part, use other materials, and select the processes needed to form it into a part. So that's the main difference. That it's you don't have to be really a Sigma Pro or Gabi user. You can do it with this BEVSIM tool.
Okay, thanks. And one more question from Angie from the SALEMA consortium. Is this tool for commercial use?
Yeah, it can be. You can get a license from us, and at the moment, yeah, we have to see that case by case.
Okay, yeah, you have the contact details, so if anyone is interested, they can contact you directly.
Sure, yeah,
I guess.
Indeed.
Okay, great. And from Mattia from Eco Invent Association, do you also include the emissions due to brake, tire, and road wear?
Yes, these are in the use phase. Yeah.
Okay, great. You have been bombarded with questions, so this means that the 2 first slots were very interesting. Sorry for that. I will continue. Can you clarify the LCA methodology you used regarding allocations for recycling? like recycled content versus the end of life recycling approach?
Yeah, it's basically what we call also system expansion, and that's translated into subtracting the avoided impacts, for instance, due to energy recovery or due to recycling. Those are then subtracted, so that's a benefit for you. And there is, it's the full benefits are then accounted to the car, to the vehicle. But if you want to have another type of allocation method in that can be included, and perhaps also important to say, we look at the quality of the recycled material. That's also accounted for.
Great, thanks. And one question for Raquel from ISQ. For the adhesive bonding of multi-material components, are you considering analyzing different types of adhesives, or is it limited to one adhesive only?
No, the plan in ALMA project is to use the adhesive developed by Rescol, is the partner in charge of developing this adhesive. So in this case, we are working with this type of adhesive exclusively. And it's working well.
This is great. Thanks. And for Tom, is the tool able to consider the different types of joining techniques?
Yeah, so there is welding, and also, for instance, with the battery lid, there will be a reversible bonding. We will get the details of that, and then it will be included in the BEVSIM model.
And one more last question for Tom as well. Which database engine supports BEVSIM?
Yeah, so of course, the database, you have the life cycle inventories, it's industry data, it's also EcoInvent and other databases, data by World Steel. But perhaps the database of the tool itself, it's developed in R Shiny, and with that we are able to present it as an online version via the Diamonds platform of TNO. I hope that answers the question.
I hope as well. One more question arrived just now. If you are planning to extend the LCA framework analysis for other technologies like electric vehicles,
Yeah, this of course, this is the CND, passenger car electric vehicles, but it's also possible to have an electric bus, for instance, in BEVSIM, and compare that with the unconventional diesel bus.
Okay, great.
Good.
So I think we have concluded with the questions as well. So I want to thank you both for the presentations and for taking the questions now.
Yeah, you're welcome.
Thank you, Raquel. Thank you, Tom.
Thank you very much.
I would like now to move to Mr. Ramon Garcia from Global Factor, who will give us an introduction to the FLAMINGo project. Yeah. Hello, Ramon.
Hello. I will share my screen in a moment. Well, are you seeing my screen? I guess. Yeah. Well, hello everyone. I'm Ramon Garcia from the Net Zero and Carbon Footprint Department in Global Factor, one of the FLAMINGo partners, and I'm here to talk about the life cycle analysis approach in FLAMINGo. And I would like to do a quick introduction of this project, and then my colleagues Jose and Ximena will go deeper into net zero and circular economy topics. So here we have the contents that we will see in this presentation, overview of the whole project, talking about the concept and objective, partners, work plan, approaches, and methodology. And we will talk about the industrial need of initiatives like FLAMINGo, and then about this LCA and LCCA approach. Then we will finalize with the conclusion from now. Well, the overview. So this FLAMINGo is an acronym for, sorry. FLAMINGo is acronym of fabrication of lightweight aluminum metal matrix composite and validation in green vehicles. The objective of the project is to develop an electric vehicle made of lighter materials while reducing its environmental impact and the economic impact too, because we are now doing the life cycle and life cycle cost analysis. We have partners around all Europe. You can see here in the map. And the life cycle analysis approach is to make a reference for the manufacturing process of the electric vehicle, then obtain all the data for the improvement of this this process with all the FLAMINGo knowledge, and then compare to the reference with the improvement of this environmental and economic impact. So we can prove that this enhancement of the process helps to reduce these impacts. So we can see now a simplified overview of the whole process in the project. First, we have the primary and secondary aluminum manufacture, where nanoparticles of aluminum and master batches are included in the material. Then we have the foundry process and the designed. These pieces are designed with topology of optimization. This process helps to reduce the amount of material used in each piece, and this reduce of material it's directly impacts in the environmental impact. To less material, we have less environmental impact because the use of material is reducing in the process. So we have extrusion or die casting techniques for making the chassis, the body of the electric vehicle, and then the final stage of the life cycle, that is the recycling of the components of the vehicle. This may be a key process or key stage, because the environmental and economic impact in the next generation of vehicles, it may the recycling will impact this in this environmental and economic cost. Okay. Yeah, the main objective is to validate and demonstrate the cost-effective processing solution for the automotive industry, not only for the vehicle, electric vehicle, instead of all the process, all the industry, as well as following the principles of circular economy and cradle-to-cradle approach. As we said before, these improvements have positive consequences in the economic and environmental performance of the process. We have like three stages of objective related with the development of technologies, demonstration activities, and market replication. And every partner, depending on their expertise, can afford every one of the objectives. The main specific challenge in this case is related to the improvement efficiency and range of electric vehicle through the production and use to recovery. We can see here the SWOT analysis, and related with the LCA topic, we can highlight the holistic approach to sustainability as a strength of the project. of the project. On the other hand, an important weakness is slow regulation and legislation processes within the European Union, and also it requires private fund and investment by the moment until it's replicated and economic sustainable in the market. About the threats, we can talk about new regulation and emission topics and environmental topics, and a changing political and environmental instability in general in the world and European Union. Finally, about the opportunities, we can reach a better use of resources and aluminium throughout the process and the whole life cycles, using new technological resources in the manufacturing process, thanks to FLAMINGo project. The concept of the FLAMINGo project is that nowadays the automotive sector, the two most used materials are steels and aluminium alloys, and the fact that aluminium alloys are an engineering solution to make more to use less material in each piece, and also make these pieces more with a better performance in the vehicle. So with this new approach of manufacturing aluminum-based composite, the objective is to make aluminum an effective substitute to steel, and aluminum recycling is extensively done, and aluminum can be recycled several times. We can reduce all of these impacts, economic and environmental, using these new alloys of aluminum instead of the steel that are using nowadays in the manufacturing of these vehicles. Not only electric vehicles, instead of all of the industry. So the FLAMINGo project will have a duration of 42 months. The principal stages are production of aluminum matrix and alloys master batches to incorporate them to the process. The redesign of the automotive parts and components using this topology optimization to reduce the amount of material used in each piece. Then the optimization of manufacturing methods and demonstration, and the phase 4, the environmental sustainability and circular economy and market issues. This is the phase 4, but we are working on it since phase 1 until the end of the project to have all the information of the possible information to this environmental assessment. You have here like an example of this, like the steering knuckle of the electric vehicle of Alke. You can see here this vehicle from one of our partners in FLAMINGo, and this is the result using less material designed with this new methodology. So this is like an example, but the idea is to extend this approximation to the whole body of the vehicle. Now we have again this little vehicle. The industrial need is like electric vehicle is supposed to be the next disruptive market force for transportation and technology and this technology. And the electric vehicle manufacturer are convinced that lightweighting is a major topic because it implies less energy to move the vehicle, and it's good for not only the money that costs move the vehicle, instead of the cost of the manufacturing and the reduction of the environmental impact in this manufacturing process. So FLAMINGo aspires to develop a group of integrated technologies that will allow this wide use of aluminum metals matrix composite in the whole automotive industry, using this advancement in technology and topology optimization and recycling process. So here we have a super quick life cycle analysis approach. We all know that LCA is a technique for determining the environmental aspects and potential impacts associated with the product on the global atmosphere, on the water and the soil nearby system to the study case. We are working obviously in a cradle-to-cradle approximation because the objective is to analyze environmental impact of the whole process. And we're working with some inputs about raw materials, energy, and water. And with these inputs, we try to figure out the performance in these stages of the manufacturing process: the production of raw materials, the production of the components of the vehicle itself, the distribution of the products, and then the use of these products along all its life cycles, and the end of life, and possibly recycling the component of the car, of the vehicle. And the outputs will be the atmospheric emission, like in every life cycle analysis, the atmospheric emission, the wastewater and solid waste impacts within the projects. In the typical environmental impact, global warming, ozone depletion, acidification of the soil and water, and all the list of environmental impacts of the life cycle analysis. We are working in the life cycle cost analysis too, not only the life cycle cost, because we have to know we have to get the less cost of manufacture of this kind of vehicle, but being consistent with this quality and function, with no compromising these topics. But it's interesting, and we have to collect data about all the process of manufacture, so we can get data of the money too, and do this life cycle cost analysis. This is a flow diagram of inputs of raw material, energy, and water. And we have the procurement of raw material, casting and extrusion, distribution, use, and aluminum recycling. And the outputs, like we said before. We have now a quick review of the aluminum value chain. This is as we said before, it's this is a critical topic, because it will determine the impact of the next generation of vehicles, electric or not electric vehicle. So in the end of life, we have the disassembling of the whole vehicle for separating the leakages and reuse of hazardous parts, the shredding for separating the fluff and non-metallic compounds, the magnetic separation for the iron, zinc float for plastic, woods, rubber, and heavy materials like high-grade steel, and the decurrent separation for stone. So we have the aluminum, and it can be used for the next generation of vehicles as secondary aluminum, and reducing the environmental impacts of the manufacturing process. To reach these goals, the project considers all the steps from the cradle to cradle, as we said before, like the component design, since the component design, the production of nanoparticles, and then the casting of the components and extrusion of profile with the new aluminum alloys. And then the use of this component for substitution of steel and aluminum parts in electric vehicles, and recycling. And once again, to reduce the economic and environmental impacts of the vehicles manufactured. And the conclusion. So the project is still under development. We have data available of the partners, but it's not the final data. So this lack of data allows us to analyze more scenarios, and we are working on it, and drafted, and we are drafting to the data that we don't have yet. But in conclusion, we have to move forward with the sorry. We need to continue collecting this information to complete the LCA and LCCA assessment with the objective of confirming the improvement in performance in economic and environmental aspects of the vehicle manufacturing, using all the enhancements in materials and procedures provided by the project. So in matter of in these topics, there are no other companies or consortium that publish this data of life cycle analysis. So this is an opportunity to transparency in these topics. Well, the preliminary analysis of the life cycle set the ground for the main environmental topics to focus on, and we move forward with this recompilation of data in this aspect. So we are working too in the life cycle cost analysis that is still pending, and we have to work on it. So this is the introduction. I don't have any question for now or after.
Thank you, Ramon. Currently, I see no questions in the chat, but we can proceed with the next presentation, and we can take questions for the both of you right after. So let me introduce Mr. Jose Manuel Correa from Global Factor, who is going to give a presentation on the circular economy application after the LCA and zero net.
Good morning to all, and let me share my screen, and you can let me know if everything is okay.
Yes, everything looks great.
Okay, perfect. So today I'm gonna talk a little bit more about net zero and the context of net zero, and then we're gonna get into depth of circular economy as a tool to achieve net zero. And this is going to be the transition to the presentation to Tom and Ximena that are going to get into depth into these aspects. So we're going to see the scientific context and political context, then companies and net zero, and the scientific path to net zero based on the Science-Based Target Initiative scheme, and then a little bit of circular economy and net zero to hand over to Ximena and Tom. So let's start by talking about the context of the net zero and climate change a little bit. So first, we will review the concept of net zero emissions and climate neutrality. What we are looking for when we talk about net zero is a balance between the... Sorry, I can... someone has a question? Or maybe... Maybe we can yeah, okay, that's it. Okay, thank you. I thought someone had a question. So when we talk about net zero, we are looking for a balance between what is emitted into the atmosphere and what we are able to absorb. This is the great challenge that we have as a species. In this sense, the IPCC, that is the Intergovernmental Panel of Experts in Climate Change, assures in its last report that it's the human activity that has led to these changes in climate and in the atmosphere, and that we must mitigate them by aligning ourselves with the international objectives of the Paris Agreement, that is not to exceed the global temperature by 1.5 Celsius. Likewise, because of these studies and these reports, the international community has also set targets for net zero by 2050. You can see it in later. We're going to talk about it in the Green Deal, in the European Green Deal, and in local regulations and laws around Europe. And this is why the UNO has driven media campaigns such as "This is the coolest summer of the rest of your life" and things like that to keep the challenge alive. And that was expressed not only in Glasgow, but also in COP27 in Egypt. As I was saying before, the main drivers to of this issue at the corporate level are like the regulatory frameworks, such as the European Green Deal and the climate change and energy transition law in Spain, for example, when I was talking about local regulations. These frameworks eventually lead companies to act on climate change mitigation and adaptation issues, as well as to set framed and regulation aligned targets, such as net zero by 2050, as had been stipulated in these directives. These obviously always under a scientific base or methodology, and that's why we like to talk about net zero within the Science-Based Target Initiative standard. Examples of these regulations can be, for example, in the European Green Deal there has an update lately, that is the Fit for 55 scheme, and also has future changes in the carbon markets, for example, and reduction targets a little bit more aggressive for companies with these new regulations. Also, the climate change and electric or energy efficiency law in Spain says that we have to reduce 23% emissions reductions by 2030, for example, and be net zero emissions by 2050. And also apart from the important regulations, other important directives that are going around lately to consider are those related to the non-financial reporting information for companies. The European Union has set a framework that is going to be applied after 2024. I mean 2025, and this is going to set a pressure into companies to start doing something about it. The UK is already one step ahead with a regulation requiring listed companies to disclose their decarbonization plans and transitions to net zero starting in 2023, this year, and there is an obligation to publish their greenhouse gas emission targets on scope 1, 2, and 3, the steps to achieve them, and the main milestones towards neutrality by 2050, in line with the international objectives. Also, external verification by a third party is needed in the UK framework. In terms of the EU, as I was saying, the CSR directive also requires in-scope companies to publish information on climate action aligned with the net zero scheme. There is also an obligation to disclose net zero alignment emission reduction targets, reduction measure plans, and budgets allocated to each measure, and offset and neutralization actions and stipulated in the framework of EVRAG. One of I think this slide, you can see the global risk horizon that we wanted to show you here is always climate change. For probably the past 2 years, the main risk in terms of environmental risks, and it also comes as third. In between 0 and 2 years, it comes as third in importance. Between 2 to 5, it comes at first, and between 5 to 10, it always comes at first too. So climate change action failure, it would be the biggest risk. That's why it's putting a lot of pressure into companies too, because to regulations to work and the public sector to be able to achieve these objectives, they have to put the pressure on the private companies so they would act on climate change adaptation and mitigation, and that would help achieve faster the objectives that are met in the regulations. As you can see, a lot of companies like like BlackRock, that is a huge financial group, decided to start drifting investors and their portfolio into a more climate-friendly framework for them, and 75% of the companies got assets net zero aligned by 2030, and that's what they want to do. We also see how stakeholders' pressure, especially investors, become an important drive to reach net zero by decarbonizing their value chain, and as well as reporting to international initiatives such as the CDP, the Carbon Disclosure Project, or align with the Science Based Target Initiative, as we previously said. At the end of the day, companies will have to get in line with these internationally recognized initiatives to meet stakeholder demands and keep being competitive. I want to talk to you now about a little bit more net zeros based on the science-based target standard. As I said before, well, it means that we have to have a balance between the emissions that we drop into the atmosphere or emit in the atmosphere and the ones that we absorb. Companies are required to set reduction targets that are based on scientific evidence and calculation methodologies. And the idea is that we can set targets for a short-term reduction targets for a short term, they would be between 5 and 10 years, and then long term, they would be until 2050 or net zero by 2050. I wanna explain a little bit how this works. First, we would talk about abatement within the value chain. It refers to emission reduction measures within the value chain through technology in line with the 1.5 Celsius trajectory. That means energy efficiency and an application of technology that helps you to emit less within your value chain. Then we have the abatement beyond a company's value chain. These are the actions taken by companies to finance emission reductions outside their value chain. These include emission offsets and should be a transitional action, and additional to reductions within the value chain. So in the moment we are here, let's say we're here, and this is our footprint. What we need to do is start reducing all this footprint by year until 2050, and at the same time we can start the abatement outside the value chain. That would be this gray area. That would be the offsetting in the voluntary markets. And then we can start at some point before 2050, start investing in our own absorption projects. So we can start creating absorptions. This the purple color, and we can start creating absorptions. But so when we get to the net zero in 2050, we can have all our remaining emissions that we were not able to reduce being absorbed by our own absorption projects. So these would be the removals, and the removals are, as I said, emission removals through carbon sinks, and nature-based solutions represent the tool that will enable the net zero to be achieved by or before 2050. So in that sense, I want to give the above given the above context, it is important that we see the circular economy as a tool to achieve net zero. Usually, we don't see circular economy as a tool to achieve net zero, but we want to get into deep about how circular economy can be a tool. According to a study of the Ellen MacArthur Foundation, the initiatives we have developed so far to mitigate climate change and reduce greenhouse gas emissions cover only 55% of the global emissions. Examples include energy efficiency initiatives and the transition to renewable energies. And the other 45% is related to production and manufacturing, and it is there where we can use circular economy and is proposed to help to reach net zero. I will hand over to my colleagues Ximena and Tom now, who will expand the knowledge on circular economy to reach net zero. And if you have any questions, we're here to respond. Thank you very much.
Thank you very much. So we can move to the next presentation then, and Tom will present along with Mrs. Ximena Franco from TNO and Global Factor, respectively. So The floor is yours.
Thank you, Ioanna, and thank you. Thanks to all the colleagues. Well, today we are going to go a little deep into the material analysis and the circularity challenges that the automotive sector presents, and the strategies for integrating this circularity in the automotive industry. This is a joint presentation with my colleague Tom Ligthart, who just presented before, from the ALMA project and Global Factor. We are talking about a contextual framework, and then the circularity in the automotive industry, with some facts and figures and some takeaway messages. In the contextual framework, I will be very quick. This is the last slide my colleague Jose just presented, talking about the big opportunities the circular economy presents for net zero strategies and the decarbonization of the sectors, such as the automotive sector. And then, based on this picture, we can also talk a little bit, or we can add a little bit about the main trends of the automotive sector. In 2022, a study was published based on a very big consultation with automotive stakeholders worldwide. And these are the main trends identified for the sector by 2030. And this is that more than 50% of vehicles in the market by 2030 will have some form of electrification. This is electrification, autonomy, connectivity, and mobility services. Mobility services are also a trend for 2030, and those are some kind of measures based on the circular economy concept. Also, that this means that there's a significant increase in the semiconductor content of manufactured vehicles. So this is very important to take into account regarding the materials issue. So this the use of these materials for the semiconductor market will be 4 times the current markets over the next 20 years. So this is a huge change in the materials demand. The current challenges for the sector is, of course, the high dependence on the supply chain, and this is shown, or this is we can use the example of the microchips shortage that currently we are still suffering. The material shortages and geopolitical uncertainty, global health risks are also and still a big challenge for any sector, and an increasing stringent environmental regulation with decarbonization targets. Finally, the scarcity in the labor market. So this can be synthesized in a high vulnerability of the global automotive supply chain. So what could be the strategies for integrating circularity in the industry? This is a general overview of the strategies, but we will go deeper into these with Tom's intervention. So there are 4 big strategies. We need to develop new models of collaboration between value chain players. in order to avoid or just to treat the enormous risk these represent. Second, the regionalizing and optimizing the supply chain. Third, ensuring a supply chain diversity also. And fourth, complying with regulations and ensuring transparency. And in this fourth part is where life cycle assessment and circularity have a most important role. Finally, from my side, I can give the floor to my colleague Tom, who is going to start talking about the material consumption in the sector. Tom.
Okay, thanks, Ximena. If you could, well, first we have this slide just to give an idea how many millions of tons are in the raw materials in the European automotive market. So that's really huge, and it's also, telling you that, well, if you can do something in the automotive sector on circularity, you can already have an impact. Next slide, please. Also looking at the discarded vehicles in the EU, so it's in 2020, it was almost, 2 million cars being discarded, and that gives also a chance to get back the materials. Further on to the circularity in the MCI and in the circularity, what you do see here, and oh no, I cannot get the point. But what is important? This is a study by Compartimento and others, and it shows what kind of circularity metrics there are already there. Metrics that focus on the resource efficiency, other metrics that more focus on the stocks of materials and the flows within the system. So again, here you have the life cycle going on the left side with the raw material extraction, and then ending at the right side at the use, and then have a loop back via remanufacturing, recycling, but also losses due to landfill and incineration, perhaps with energy recovery. So, for instance, you also have indicators that focus more on at the product level, like the MCI by Alan MacArthur, and just highlighting some things. So at your right-hand side, you see that, well, at the end of life, there is a potential for recycling, or even a potential for remanufacturing, and you have to include that in your material choice, but also in your design. So can, for instance, the body in white be reused to make a new vehicle out of it? Another approaches, of course, that's more at the beginning of the chain. So the circle at 14, it pops up at several places, but it's the input of secondary materials. And of course, there also the industry is looking for possibilities of that in steel and aluminium, but also in the plastics and all kind of other materials that are being used in a vehicle. So if you are able to increase that secondary content of a vehicle, you're also on the way of becoming circular. Then things that are more on another level, that 15 and 17, for instance, that these are things about the reuse of parts? Are the parts easy to be reused? Can you do remanufacturing or refurbishment? And of course, ease of recycling. And also in BEVSIM, we saw that there will be debondable joints, for instance, the battery lid on the battery package, so that you can easily remove it at the end of life states. And another thing is that's on a system level, can you make a stable system so that once a vehicle is in the end of life, is there a system there that can make optimal use of that end of life vehicle? So that on circularity, many indicators. Next slide, please. Alan MacArthur Foundation, they developed a material circularity indicator, and it starts with the virgin feedstock, but also you have accounting for the recycled feedstock. Lifetime is also an aspect to be included. So if you can give your product a longer service life, then that also affects material consumption, circularity in the economy. And can you really get components and materials back to be included again in a new vehicle? And so the MCI, it considers the virgin feedstock, recycling efficiency, also the leaks in the system, unrecoverable waste, and also the use of the product, intensity of use. Yeah, please. So in BEVSIM, this is a way to express the material circularity indicator. At the right-hand side, you see the total, and you do see that at this moment, the default battery electric vehicle and the ICE vehicle do not differ that much in circularity. And of course, it has to do that there are lots of metals, and for metals, we have a well-established recycling system, also, of course, driven by the value and because of the properties of the metals. So with that respect, circularity is already at a level of 0.6. Next slide, please. Then we can also look at the MCI and LCA results. Of course, to keep materials in the loops, you need also input of energy, for instance, for steel in the electric arc furnace to remelt it and refine the waste steel. The same, of course, for aluminium, but also especially with plastics, you have mechanical recycling, but you're going to chemical recycling in the end. What you do see in this picture is that the BEV is at the left-hand side, so with a circularity of about 0.63, and expressed there also the normalized environmental impacts. The difference in circularity is too small to be significant, but you do see that if you include the use phase, at this moment, the battery electric vehicle has a better performance on climate change, but for instance, for particulate matter, the performance is a bit less. What we can also do is, if we exclude the use phase, that's in the next slide. So then you see that, especially because of the battery included, but also in this case, because gray electricity was used, the environmental performance of the battery vehicle, it has the higher score. So in this case, it's the lesser environmental performance, the highest impact, the somewhat lesser performance on the environment. But of course, because the use phase is important, you have to go to green electricity, and these kind of effects have also been shown in other studies. And next slide, please. So we had that material circularity indicator. We are also looking at to have the circular footprint formula that was developed for use in the environmental footprint, product environmental footprinting by the EU. It includes the material aspects, virgin material, secondary material, but also recycling and the quality of the material that is being recycled. So that's also of importance. Can you keep your quality of your material even if it's being recycled? But also things like the energy consumption in the life cycle and credits for the energy recovery at the end of life. And then, of course, you may have some remaining waste that becomes final waste, becomes a landfill. In this circularity footprint, it's quite some formula. The factor A, for instance, is of importance. It can have values depending on the type of market between 0.2 and 0.5 by default, and if you have 0.5, burdens and benefits are equally shared between the life cycle delivering the waste product and the life cycle using the recycled materials. So that's also a type of allocation. Next slide, please. The takeaway messages, and as Ximena already mentioned, semiconductors, electronics will become more and more important in future cars, and also, of course, the battery system. In these electronics and in the battery, there are critical raw materials, and critical raw materials, I think that's especially a point to focus on in circularity, because it will be a bottleneck for further development, especially the demand for green electricity. Critical raw materials are a hurdle that will slow down the development of wind power. And as said, we've shown that there are, nearly 60 or perhaps even more circular economy indicators. They are still under development, and you must also include energy in that, I think. What are the efforts you need to keep a material in the loop? Because in some cases, the environmental performance becomes worse when you have to do too much to keep a material in the loop. And so circular and environmental performance may not always go the same way. The circular footprint formula, it does include the energy input, and so that's really a benefit for it. And as already mentioned in this presentation, giving a car a longer service life, design for recycling and design for remanufacturing and refurbishment, they are also important to increase the circularity. A last message, so all these circularity measures, they should also consider the regeneration and restoration, making ecosystem services visible for the value chain. So take the environmental performance also into account, not only look at circularity, but use them all. So this was the presentation by Ximena and by me.
Thank you very much to both of you. I see in the chat that 2 questions have arrived. So the first is for the both of you regarding to plastics usage in the car industry. How does the industry faces towards bioplastics, and is plastic and environmental impact hotspot?
It could be an environmental hotspot when the mass of materials is increasing. Also, you see with compounds that they are not always with mechanical recycling. It's very difficult. So you have to go to, for instance, chemical recycling like dissolution, sulfolysis, pyrolysis, but still you do have losses there. And as said, you also need to input energy and materials for this type of chemical recycling. And what we do see in other sectors that use plastics, for instance, in packaging, there is really now a focus on mono materials but also designed for recycling, so that the things you are making out of plastic can, for instance, be different polymers can easily be separated mechanically, and also can be recycled while maintaining the quality of the plastic, because that's of course is also an important factor. You don't want to have downcycling or at least avoid it to as much as possible.
Thanks again. So regarding the MCI, is this an indicator for projects to be able to enter the market, or it will be forbidden in the future? Is the next question from Marlamatenia Kopliotti.
Yeah, so with the material circularity indicator, you can beforehand have an idea how your circularity performance will be. It's not required, but for instance, also the circular footprint formula that I showed, for instance, in product environmental footprints, following this European environmental footprint, there the circular footprint formula is included, and so then it shows up, that kind of circularity then shows up in your LCA results, not as circularity as such, but as the environmental performance of becoming circular.
Great. One more, I think is also for the both of you. Circularity and best environmental option at the end of life are not always aligned. So what would be your recommendations to get a better alignment of both goals, like greener and more circular?
Yeah, perhaps if you, I can answer, but you can add, of course, Ximena. As said, with all kinds of composite, multi-material parts in the car, it's important that you also have the recyclability in mind, so that you can easily separate components of different materials, so that each material can into their own most beneficial kind of recycling scheme. So that is of importance. And as said, of course, it's a consumer product, but things like remanufacturing, refurbishment. I think refurbishment is well, In some sectors, it's already there, like copying machines, but perhaps it could also be part of the automotive industry. Still, the consumer wants to have a new car once in a while.
Tom, I would add there that this is a very good example of how important is the taking into account environmental footprints and environmental impacts since the design phase. So circularity and environmental footprint would be more together if we take into account the different environmental impacts since the design of the products, taking into account all the steps of in the life cycle of any kind of product.
Thank you both for your replies. And thank you everyone for the interesting presentations. I am very happy for the engagement of the audience and for replying to actual questions and for sharing your knowledge on the topics. If we do not have any further questions, I don't know if there are any more to come for the next 4 minutes that we have. Or we can conclude this first session a little bit earlier, if this is okay with you. According to the agenda, we have a short break now, and we can all meet back at 12:05. There's no need to log out. You can stay connected, mute your microphones, and we will see you at 12:05. Okay? Thank you all for being here and looking forward to the next session after the break.
Okay, see you later.
Okay,
See you later, everyone.
Welcome back, everybody, I hope. It's 12:05, so we will try to resume our program now. Perhaps I can take the opportunity to tell you what's still left on our program first. We will have now presentations from SALEMA, and then also from the rest of our Enlight TV cluster partners, including Fatigue for Light, Revolutions, and the LEVIS project. We do hope that you've managed to stay with us for all this time. Again, let me remind you that there is an opportunity to ask questions. Please write them into the chat, and please also indicate your name and your organization, and also to who the question is aimed for. If we have enough time at the end of each presentation, we will go through the questions. If not, we will try to address them at the end of the program. So please stick around for that. Otherwise, let's not waste any more time. And I would like to first introduce to you the presentation from SALEMA project on modularity in LCA by Mr. Christian Leroy and Francesca Cavezza. Can I hand over the floor to you, please?
Okay, thank you, Jose. I hope you can hear me. So I'm Christian Leroy. I'm from European Aluminium. I am in charge of innovation there. And yes, I will give you a presentation with the help of my colleague Francesca Cavezza, who will complement my introduction. So yeah, we will focus on the SALEMA project, but first I will give you some words about the aluminium industry, so the European Aluminium Organization, also a few words about the Innovation Hub. Then highlight what we mean by modular LCA, especially for aluminium, but this is obviously valid for all types of material and LCA, let's say. And then we will go into deeply, let's say, the SALEMA project and also the so-called product category rules that we developed to be used in this context of the SALEMA, and this will be addressed by my colleague Francesca Cavezza with some concluding remarks. So, few words about European Aluminium and its Innovation Hub. In fact, European Aluminium is the association representing the aluminium industry in Europe. So we have alumina producers, we have primary aluminium producers, but also those transforming aluminium, especially so-called rollers, so in flat products, and the extruders in profiles. And then we have also the recyclers, those remelting, refining aluminium into new products. So this is typically our members. And you can see that we have more than 90 members in Europe, representing more than 600 plants. So we are, let's say, well distributed. And in terms of application, it's not surprising that you see transport as a winner, let's say 40%. So this is typically why this LCA workshop today on transport is very important for aluminium. But building is quite important as well, and packaging. So within the association, we have 3 market groups dealing specifically with these market applications. So developing projects, also advocating for aluminium in those for those applications. Europe is maybe not so central for primary production, but in terms of recycling is already well implemented, and about 50% is, let's say, sourcing from recycling in Europe. And it's clear that recycling rate is high in many areas, especially for building and automotive. So if we move to the innovation hub on the right-hand side, okay, this is a kind of a small, let's say, a smaller group within the association. Here we group 18 members, also the market group. So and the idea is to really work together on innovation, so in a collaborative manner. We map R&D challenges along the value chain. We also engage with different PPPs, for example, you may know Processes for Planet, made in Europe, or Built for People. These are typically those public-private partnerships we work with. And we organize workshops, collaborative projects, studies for members, and we try as much as possible to trigger EU projects addressing the European, the aluminium value chain, and we facilitate access to that. So currently we are running more or less 12 collaborative projects. Some are Horizon 2020, some Horizon Europe, also project directly financed by members. So it's yeah, typically what we do there for members. Maybe next slide. Yes, so this was a brief overview of our activities, but the topic of today is about modularity. So and within European Aluminium, we are active in LCA. We develop life cycle inventory data sets for the various processes, for the production, for the recycling, for the transformation. So if you are interested, we can provide those data sets and provide a report related to that. But the topic today is more about modularity. And in fact, we were quite active in the last days, in the last years in CENEX 350. And maybe about 10 years ago, we developed this so-called Module D, which is, let's say, addressing this modularity, because there the idea is standards which are developed for building products and under CENEX 350, so Building Sustainability Committee. We address in a Module A first the production stage, then we have a Module B addressing use stage, then a Module C addressing end-of-life stage. And what we also added to that is a module that look at the full picture, the full life cycle, and address the additional benefits resulting from the whole life cycle from the end-of-life stage, in fact. So this is, let's say, something that we allow us to really get the full pictures in terms of life cycle, because typically the Module A address this through the so-called recycled content, meaning that you don't get the full picture. And this Module D calculate then for the additional quantity of secondary materials you produce these additional benefits. So we feel that this modular approach provide more transparency, is more, let's say, adequate, because you can either optimize the production phase, so reduce the impact, but on the other side, you can also look at what it gives from a full for design for recycling, because you can also reflect the additional benefits you get from end of life, so that you get the full pictures, and you can, let's say, allocate the environmental impacts burdens where it really takes place, let's say production, use, or end of life stage. So this is, I think, really what we would recommend if you need to use a modular approach. And in this SALEMA project, this was needed. So it's why we really recommend to use this approach in this type of project. So maybe the next slide to explain basically what we mean by that and how it works. So if we have a product of 1 kilogram, so yeah, to make it simple, so typically in module A we can have different sourcing, let's say, and we can have a primary metal, so primary aluminium on one side, but also a fraction coming from recycling. But then at end of life, you can get, usually you have quite high recycling rates because it's quite a valuable and interesting material to recycle, aluminium or other metals. And then you see that you have a discrepancy between what you get at end of life and what you have as a recycled content, because typically today the scrap availability is the bottleneck. So the average recycled content you have in products is usually lower than the so-called end-of-life recycling rate at end of life. So you have this discrepancy. And then to address that, this is through module D, so that you address the net surplus, the net production. Could be a consumption, but usually it's a production. And then you reflect the additional benefits you get there by, let's say, calculating the substitution you can have through this recycled material you generate from your full product life cycle, because you are a net producer of secondary materials. And obviously you avoid double counting by using this net flow of scrap you generate at end of life. So this is the logic that we use in the building context, in the building sector, and we propose to use also in these SALEMA projects that will be highlighted now by my colleague Francesca. So please, Francesca, the floor is yours.
Thank you, Christian, and hello, everyone. So we'll shortly introduce the SALEMA project. A bit first, it's a European project. It includes 16 members in the consortium, and it's coordinated by Eurecat. We have been discussing a lot this morning about how the Green Deal really pushes towards a higher amount of electric vehicles. And because of the properties of aluminium, this will most likely introduce as well to a higher content of demand as well of aluminium. What was highlighted but already before, but it's maybe not so obvious, is that there will be more and more need for critical raw materials, and we have to be sure that those materials are not critical anymore, so that we reduce really the dependencies on imported raw materials. And this is a bit the rationale behind the SALEMA project. So the scope of the project is to reduce dependency from primary magnesium and silicon in aluminium alloys for electric vehicles. Magnesium and silicon are two alloying elements which are extremely common in vast majority of aluminium alloys, because they confer quite some properties to the final product. So how to reduce this dependency in two ways that we can see as a parallel. From one side, by reducing the amount of silicon and magnesium in the and having like new novel alloy, and the other side to really increase the recycled scrap metal rate in the aluminium alloy. So to have this magnesium and silicon not from primary sources anymore, but really from recycled scrap. And to do so, we in this project integrated as well a sorting system that improves the sorting of aluminium scrap, and it does that with a combination of different techniques. You can see here the demonstrator that have been used in this project to prove a bit the feasibility of this project. So there are more or less like a structural part of the vehicles, and includes as well a battery box. Now, what's the role of European Aluminium? And that's why we are here as well. Beside communication dissemination and looking at the policy landscape, we contribute by developing as well a product category rule for this project. So what's a product category rule? I will be very short. It really gives us the guidelines of how to make a life cycle assessment, and gives guidelines on the methodology that needs to be used in order to have a more even coherent life cycle assessment that are and APDs that can be then compared one to another. As a first point, so the first, these product category rules. So it's a product category rules for aluminum component for passenger cars. I wanted to show the system boundaries, which is a bit reflecting a bit what Christian has explained before with this modularity approach. So we have the module A, which includes what we call the upstream and core. So really the material sourcing and manufacturing of the component until really the assembly of it in the vehicle. Then we have the module B, which is the use stage, the module C, which is the end of life processing and disposal according to what is done, and then the module D, which is the module that, as Christian explained, really looks at scrap which is generated outside the system boundary. Thanks to this modularity approach, it's possible, modular approach, it's possible to develop EPDs, like different kind of EPDs. So cradle to gate, so looking only at module A, a cradle to gate approach plus the end of life stage, including the additional environmental aspect resulting from end of life stage. So we have module A, module C, and module D, and then an approach really cradle to grave that looks at the whole, the most complete picture of it. Also includes as well the use stage. As I mentioned before, that really SALEMA, the SALEMA project is really looking at critical raw materials such as magnesium and silicon. So for us, it was important to include as well alloying elements in the calculation on the environmental impact. Now, Christian mentioned that European Aluminium has already data set that were developed for aluminium, and there is even a link here that you can find, or you can send us an email. But most of the time, does not really consider alloying elements. It considers as 100% aluminium. So we decided to add this in the product category rule because it's really important as well for the project. And how are these elements considered? So only elements which are intentionally added are considered in the life cycle assessment, only the one exceeding 0.1, and then everything that respects the two before, and then it does not come from the scrap pool, then it will come from primary sources. And I'm out of time, I will be short, but there are two examples as well, a bit like and similar to what I've seen before, to see really what is even the added value of having, considering like this modularity approach with the module D. So we have two examples in which we have a product which has aluminium and silicon. We put only silicon, but of course, it's exemplary for different alloying elements. So we have 1 kilogram of product, and the source, there are two different sources that we consider. So in the example 1, we have a lower amount of recycled scrap, and example 2, we have a higher amount of recycled scrap. And then the same amount of scrap, it's recycled at the end of life. And then when we adding the module D, it really gives an idea of the whole impact and different impact actually that these two examples give on the whole life cycle, and that's why we consider it's important to have a full picture to add this module D. So the conclusion is that we believe that by using a modular approach, the LCA can be more flexible, transparent, and standardized process. And adding a module D in this modular approach really can give a full picture into the additional benefits that coming from recycling from outside the system boundary. This was applied as well for the product category rule that was developed for the SALEMA EU project. And actually, we only do the product category rule, and then the LCA will be, when we developed this in collaboration with the member of the consortium, but the LCA will will then developed by Eurecat, which is actually presenting for another project just after us. So from Violeta as well from Eurecat. And then additional of alloying elements have been considered as well in this product category rule. Thank you.
Thank you very much for that presentation. We are a little bit out of time. There is a question, so I hope that we can have time to address that at the end of the program, because we have to move on. So please stick around with us for that. I would like now to move on to the Fatigue for Light project, which will be presented by Ms. Maria Violeta Vargas Para from Eurecat, and she'll be talking about the strategy on LCA for that project.
Yeah, let me share my screen, and thank you both of you for presenting me, Francesca and Jose, since you both presented a bit who I am and where I work. As they said, I work at Eurecat, and we are part of both projects, SALEMA and Fatigue for Light for now. And well, for now, I'm going to present a little bit what we do on the LCA strategy for Fatigue for Light. First, I'm going to explain a little bit what it is, what we're doing on Fatigue for Light project, what are our main objectives, and what we're studying. And then I'm going to present a bit of what we've done applying life cycle thinking and the eco-design methodology, and then the scope and functional unit system boundaries, more directly on the LCA approach. And then how we're doing on the LCA data collection that we all know is kind of a hassle. So Fatigue for Light has a few main objectives, which is a weight reduction of 24 to 30% of this weight. Also is aiming for weight savings from structural vehicle weight of 12 to 15%, which will also increase the electric vehicle safety due to reduced front mass. We are also aiming to find material solutions with high fatigue performance, such as advanced high strength steel, stainless steel, aluminum alloys, and hybrid materials with fiber polymers materials, to develop also a new computer modeling with high fatigue prediction accuracy, new experimental methodologies that can reduce the testing time for these new materials. And then more on our side of LCA or life cycle thinking, we are looking for an enhanced affordability and sustainability that is based on eco-design or design for circularity, supported by the studies of life cycle assessment and life cycle costing. So for this project, we are on the life cycle thinking part, we are doing design for circularity, life cycle assessment, and life cycle costing all at the same time, and all throughout the project from the beginning. We are studying this, just like SALEMA, that has a few demonstrators to prove all these developments. We are studying these 4 demonstrators, which is the lower control arm, the crossbeam member, the wheel, and a lab scale demonstrator to prove the different materials that we're trying on this project. So the LCA is going to be applied to all these demonstrators with the different materials as well. And for this, at Eurecat, we developed a new methodology for eco-design or design for circularity some time ago, and we applied it to different projects that we are working on. One of these projects is Fatigue for Light, the other one is Marble, but we're not presenting that one here. For Fatigue for Light, we use this methodology that follows 4 simple steps that actually are following the Deming cycle, which is known by a lot of us, and it's like easy to think about it. So it's plan, do, study, and act. And following this methodology, well, we have 4 steps that are easy, where we identify different hotspots or the aspects that we have to really pay attention to, that we're going to get really bigger results than others. Then to establish different strategies based on eco-design and based on what we found on step 1. After this step 2, where we have the strategies, we have to readapt the strategies to the technical aspects and requirements of whatever we are designing. And then on step 4, we define concrete and specific actions, eco-design actions to apply. A little bit more in detail, on the first step, what we do is based on a benchmark analysis and on a simplified and preliminary LCA and LCC of this, after having these results of this preliminary and simplified LCA and LCC, we can identify these hotspots and the life cycle stages, and then correlate these hotspots with the life cycle stages to find where we have to pay attention to. And after having this hotspots defined, then we can define the strategies that we're going to go to. In this project, since our main objective is lightweighting, then we focus mainly on it, but we also try to pay attention to other objectives like design for maintainability, lifetime extension, to find substitutes for critical raw materials, and to consider second market resources for this. So after going through step 2, we have a repository of strategies in a datasheet format that we can actually apply to other projects as well, as long as they're electric vehicles projects. So having this repository of strategies, we had a webinar or workshop where we invited all our partners from Fatigue for Light, and we try to familiarize everybody with the eco-design concept so we can came up with more ideas and to readapt the strategies that we had at the beginning, to readapt them to the technical aspects and requirements that only the technicians can know. So then we had a different set of, well, not different, but a more accurate set of strategies. And after the strategies, we defined specific actions to go through throughout the project, as well with all the partners that were participating in the webinar. So after having a list of different specific actions that we can go through, we also applied an analytical hierarchy process, which is a methodology to rank things, like to put them in order, which one is more important or more feasible and viable and important at the same time. So with all the partners, we ranked these actions, and we got like a list of actions that we have to follow through. And also that since they're ranked, then we can identify the most important ones. So we came up with this list. Over here, you can't see the list in order because we wanted to show you the strategies and the actions at the same time. So you can see here on the left, the list of the strategies that we were considering. And then we have the list of the specific actions that we're going to go throughout the project to get better results in circularity and environmental impact, hopefully. Then we have to do another LCA and LCC and compare the results with the first ones or preliminary LCA and LCC that we started with. So then with the AHP, well, the analytical hierarchy process, we have a score for each of the strategies, and then we did the same for the actions, and we have a score for the actions over here, and then a final score combining the two previous ones. And then with that score is the one that helps us put the actions in order. So, well, that's for the eco-design methodology. And then to show you just the scope that we are following in Fatigue for Light, we have 3 life cycle stages considered in this project. We have one that is raw material extraction, manufacturing, and assembly. Then we have the use phase and the end of life. Of course, we are following a cradle-to-cradle approach on this project. And for this, we have, well, a functional unit of 1 kilometer. And we have this system boundaries that are like this one that you can see on screen is very general. All the processes from raw material extraction, manufacturing, and assembly will be specific for each of the demonstrators once we have the inventory for each of them. But just to show you, this is the general one for all the demonstrators in the studies. I think I have nothing else there. And then right now we are collecting the data for both the LCA and LCC at the same time. We've been sending this template to all our partners and getting some answers from them. Sometimes it's easier and sometimes it's kind of hard to get an answer. And other times it's hard to fill in this table the right way, but we're working on it. We have a very good consortium, so we're all working on it. They're all implied in it, thankfully. So after having all this data, we have all this data for the first stage, that is raw material extraction, manufacturing, and all this. And then we have the use stage and the end of life stage that are going to be based on literature. For the use stage, we're going to use these two references, which is one of from the CSA group. I think we all know it. It's for auto parts in general. And then there's the European Environment and Agency document or guidelines as well that are specific for electric vehicles. So we're going to use these two for the definition of the use stage, which is going to give us the lifetime driving distance and the energy consumption throughout the life. And then for the end of life stage, we also have to define the different percentages for recycling, landfilling, and energy recovery based on literature for this too. After applying this this eco-design methodology and the LCA at the beginning and all, we have found that, again, the LCA data collection is challenging. It's been a hustle and it still is. The difficulties, again, here is the definition of the use stage and the end of life, because it's always kind of, it's accurate to get a definition from literature, but it's still, we are worried that it's not real at the moment that this information is applied. If we applied it right now, I'm sure it's going to be more or less real because this literature will be up to date, but at another moment it will be different. As always on LCA, this happens often, but still, it's a worry. And then from applying the eco-design methodology, we found that we could find a very useful list of actions to go through throughout the project. So we found it very useful. So that would be it from my side.
Thank you very much for your presentation. At the moment, we don't seem to have any questions for you. That might change, so please stick around. Okay. And we will have a session at the end where we have more general questions, if not for all of our presenters. So we will make use of the time to go on to the next presentation, which is from the Revolution project, who will also be presenting on their strategy, general strategy, and on their LCA in specific. And I would like to welcome from IDENER, Mr. David Servian Rivas. You are on mute, I believe.
Now?
Now we can hear you.
Okay, perfect. I'm going to share my screen. I will try to be a little more straightforward. Wait a minute. Okay. So, as he said, I'm David from IDENER. I will present the Revolution project and what is our LCA point of view for the project. So first, I'm going to start with a general project overview. As you know, we talked before, in the actual automotive system, we have a principal fossil fuel basis automotive, with the problem we have with the not just the fossil fuel, also all the residue we generate when we discard the car. We will try to move to the electric system, to the electric vehicle system. However, we still have one of the principal problems is we also need batteries, but also we still we produce residue from the car with this car. In the Revolution project, what we will try to do, or we are working on, is to maximize the recycled material into this system, the electrical vehicle system. Also, for this, we will deploy new innovative material. We deliver safety into the cars. Also, we will try to reduce the weight of these cars. Also, the recyclability. And in addition, we will design this new piece with the new material with easy disassemble design. However, one of the principal problems with these new recyclable materials is the material consistency. As other people has mentioned before, this material has the problem when you try to recycle and reuse it. The material is quite difficult to reuse because they change the characteristic of the material itself. So in this project, also we will use an AI control strategy in order to improve in order to avoid this problem with the consistency of the material and increase in this way the recyclability of the materials. So we will go to this system, to the new system, reducing the and reduce the amount of material go to the landfill, increase the recyclability, introduce again the system, and try to reduce the impact of the electrical vehicles. So for this purpose, we are working 4 cases. 2 of this new piece of the car made of this new material will be substituted an steel material for a new, in this occasion, for a new polymeric material, recycled one. We are working, they are still working in choose which material is better for this purpose. Also, we select other 2 piece made of polymeric material and substituted by again for recycled material. Also, with the objective also we reduce the weight of the car. From our LCA process, try to do a cradle-to-cradle strategy in order to take into account all the manufacturing steps, the use and the end of life strategy, also the recycling step, in order to have everything. What we're gonna do is to compare the conventional system, the conventional way to produce this piece, with the revolution system. So in order to do that, I start to do the conventional production system because we don't have any information or there is no LCA specific done for this piece. So I decide to go with the recycling methodology because I have more experience with this methodology. Also, we're using the SIMAPper software, and all the impacts are being calculated by per piece. So when I started to do all this conventional LCA production, I said, okay, I will start to asking for all the information I can from my partners. The problem was that my partners are quite sorted. I mean, most of them are in the production of some of the material, some of the manufacturing, and also we have a partner in the assembly part. But we don't have information in the raw material production, even if we don't have information about the use of the car, or even in the end of life. So I start with the principal one big problem is I don't have information for most of the system. So what I do is ask for information to my partners if they know any information of this system we don't have. Also, use the database like Coinbase, World Steel, or Plug Steel for Europe in order to fulfill this gap of information. And also ask about the distance of the transport. Why? Because most of my partners most of the partners in this project are across the Europe. We have people from Spain, Turkey, Germany, Finland. So at the end, this transport step will be really important. So we need information about how long these material are moving around Europe in order to take into account this impact. So when I take all the information they can give me, I say that the first study I did was a cradle to gate instead of a cradle to cradle, because I don't have information of the end of life or the recycling step. No of my partner are working on it right now. So in the cradle to cradle system, in the cradle to gate system, I saw that from the LCA summary, the raw material production is the principal source of most of the impact, being the global warming the most important one. The transport material start to be really important when the distances are quite really high, not because it's not an important step, it's because of the raw material impact. And one thing that surprised me is the assembly part. The metal material are welding to the chassis, so this impact affects a lot to the workers from our point of view. So all the electricity, the fume producing in the welding have important impact into the human toxicity. This is important because at the end we will try to change all the metal part with polymeric piece, and for this polymeric piece we will use it in the chassis. We put it with the chassis with a glue or adhesive. So maybe not just the material itself, also how the material is put it together with the car is important. But our conclusion is what the problem with the machinery impact is not taken into account. What I mean is that when I ask about information of the process, about how much material they are using, I've found that most of my partners have a lot of information, but don't have every information you will need. The machinery is not taken into account because at the end they don't know how much we have the equipment they use, how much metal have the equipment they use. And I decided to not take it into account because at the end we need to start to have some information about the process. Maybe this in the future will be added, but right now I don't take it into account. Also, I don't, in this occasion, when I finish this analysis, what I thought is make it, I don't know if I'm gonna take into account the impact of the use of this piece into the car. What I mean is, okay, the car will be lighter, but in order to take the effect of change this piece with these new materials, I need a lot of information, or I need the people that build the car do a lot of investigation in order to see if the weights produce less impact because they use less energy, and it's because we reduce the light of the weight of the piece and so on. So in the final, at the end of the project, I don't know if the use of this piece will be added into the LCA. For now, this is all the work I done for now. In the future, we have to add the information of the recycling and end of life of the conventional product, and also I have to do all the system for the revolution innovation. That is all. Thank you for your attention. If there is any question.
Thank you very much for your presentation. That was very interesting. At the moment, we don't have any direct questions for the Revolution project, but we will, as I said, save more time also at the end of the project for any other questions we may have. So we will move on to our next presentation, which is from the LEVIS project. We'll be presenting on the strategy and their LCA. This is from the organization CENEX, Mr. Floris Teunissen. Can you please take the floor?
Yeah, will do. Just share my screen. Can everybody see the screen?
Yes.
All right, thank you. So I'm going to present the LEVIS project and how we perform lifecycle analysis. So first I do a little bit of an introduction on what we do at LEVIS, what is the idea, so a little bit of context, and then I will show you our strategy on lifecycle assessment, and it's more like a wide strategy on sustainability assessment and circularity in general. So first going over to LEVIS. So we are making lightweight materials for components that are used in electric vehicles. And we design these components by the use of eco-design. So we integrate circularity already at the start. In that case, we also consider the end-of-life strategies and the production as well as the use phase of these components. So here are the demonstrators and the partners listed of our project. So we see that we are having 3 components. Demo 1 is the suspension control arm. Demo 2 is the battery box containing the batteries. The batteries themselves are not taken into account in our scope. And Demo 3 is the cross-car beam. So we have separate partners designing the components, and we have partners, we are experts in the materials themselves. So the materials are bio-based carbon fiber reinforced plastics. They have expertise in them, they have experience in them, and they also know how to manufacture these materials. Then we also have partners concerning the end of life of these materials and components. We at CENEX Netherlands, we are responsible for the circular economy approach and the life cycle assessment. So our objectives in general, so the idea of these components is of course to make them lightweight and sustainable. So our goal is to have a 25% reduced global warming potential at component level and 7% at vehicle level. We also look further ahead, so at other components of the vehicle. So what if we use these LEVIS technologies, so these materials and manufacturing processes and end-of-life processes, what would happen to the overall structural weight? And our goal is to have it at least a potential of 25% weight reduction over the whole vehicle. We also look at making these materials in a cost-effective way to assess the feasibility of these products. So with a large-scale operation, they could be at least be comparable in terms of cost efficiency to any current available solutions. We use advanced simulation methodologies to improve structural integrity and life cycle predictions. We have sensorization and monitorization technologies. And of course, what I mentioned before, we use end-of-life approaches for the assessed materials and processes we are considering. So going on further ahead on the specific life cycle strategies we use on LEVIS. So what I want to go on first is the eco-design approach. So we start with circularity at the start of the design process. We did that in the same time frame as with the design of the products. And we developed a tool, and this tool is called the IEDGE toolkit, which stands for Integrated Eco-Design Guidelines and Evaluation. The idea is that it's used during the design process. And if you consider the design process as a 5-step method, where you have product planning, you do research, you have the design concept, and you have detailed design, and then at the end you have the final solution. the idea is that this toolkit helps you during the first 3 phases. So product planning, the research, and the concept of the design. So the detailed design and the final solution, that's a later part of the design process, but we want to at least bring the concept of circularity and circular economy during the first stages of the design process. So how do we do that? As mentioned before, we have developed an eco-design toolkit. And this toolkit is made to be integrated into the design process. So it's not a separate part. And what I mean by that is that it does not focus solely on the environmental aspects of the design phase. So what you can have most of the time is that you have a separate part that is designing only the technical aspects. Then you have a separate part of the design team which looking at the economic aspects, and a separate part which may be looking at the environmental aspects. We wanted to have it integrated all together so you can actually make decisions based on these the 4 focus areas, which are environmental, economic, technical, and social. This makes it easier to make decisions based on these focus areas, because you can weigh those different areas to each other and see for yourself which are important and which are maybe less important, based on what is important for your company, what is important for the customers, etc., etc. So at the end of the usage of this eco-design toolkit, you will have a decision on where to go in your design process, and you have a documentation and justification for why you have chosen these design improvement options. So we developed this toolkit. We also used it, so we already got back some feedback, which is all reported, and we saw that it actually helped for the designers. It made them especially more aware of those different lifecycle categories and those 4 focus areas which I have mentioned before. However, of course, we also got some feedback, and by that we could make the tool, for example, easier to use, and by that reduce investment time to learn the toolkit, because it's a very large tool, so to say, and it takes time to actually use it, and yeah, there's some investment in there. It has a learning curve, so to say. Throughout the project is not finished. There's still a year to go, and we'll have additional follow-up moments to see if these circular economy principles are also actually used in the rest of the design phase, if we stand by those decisions, and what is the actual effect of these circular economy principles that are now in the design. The results are not in yet, but that is planned for the next year. So further on how we perform life cycle assessment, it's basically 4 pillars. So we have the life cycle assessment, we have the life cycle costing, then we look, as mentioned before, the replication opportunities of the LEVIS technologies. So what could we use those LEVIS technologies for other components? And also, if we have a more lightweight vehicle, what is the effect on our EV motor efficiency, which also impacts at the end the life cycle impact of the product. Going over the life cycle assessment, I will do very shortly in how we do it, because it's mentioned in the other projects before, a lot about the scope. So of course we looked at the full life cycle, so the raw materials, the manufacturing, the use phase, and the end of life, and the recycling of the products. So we do that with a comparative LCA. So we have the benchmark products, and the benchmark products are now made of steel and aluminium, and our demo cases are made from the bio-based carbon fiber reinforced plastics, and we compare them to each other what is the full impact, and where are the big changes in that case. So we would like to see, of course, in the use phase, because they're more lightweight when they're used in the car, that we see some lower emissions. But what happens during the production? Is there more energy involved? Is it harder or easier to recycle? Are the materials downgraded? That's we all want to bring map, so to say, with the life cycle assessment. Of course, we also do a sensitivity analysis, because we all know that we have to make a lot of assumptions during the life cycle assessment. So here we see 3 examples of the sensitivity analysis of parameters we can use for this. The first one is the energy use. So the products are made for electric vehicles, and they can be charged with of course, green energy, so mostly from solar and wind power, etc., etc. And we use different electricity grid mixes from different continents to showcase what will be the effect of lightweighting the vehicle and charging the vehicle on in these continents. We also look at different recycling rates. So this is more of a what-if situation. So what would happen if the recycling rate of the products would be higher or lower than is currently the case? And we also have parameters of the lifespan of the vehicle. So it also depends, of course, the longer you use the vehicle, the better, the more emissions you have on the use phase, but the more effect the lightweighting of the components has. So these are all parameters we play around with, and we have a sort of range on how the life cycle assessment operates. And at the end, as mentioned before, we see what the effect is of using the eco-design toolkit and implementing circularity and circular economy principles at the start of the design phase. If we look at life cycle costing, so what are we trying to do? We assess the cost implications also from a life cycle perspective. So we use the Gabi model. We use Gabi for our life cycle assessment, and we use the same process flow diagrams for the LCC as we've done for the LCA. So instead of using emission factor and energy factors, etc., we use cost factors, and we use it in the same Gabi models that we have the same scope as for the LCA and as we have for the LCC. We acquire data based on flow cost, machine cost, and personnel cost. This is acquired by the partners themselves who manufacture these components and also do the end of life of these components. And by that, we want to demonstrate that it's not only more sustainable, but it's also actually economically feasible to produce these components. Then the third pillar is our replication opportunities. So what we do, we look at our LEVIS technologies, and we establish criteria based on the material properties of these technologies. We use that so that later on we have a list of potential replication opportunities, and we can see if these materials could actually be used for these specific causes, for these components. We do that by a collective brainstorm session with our partners. These are also all expert partners within their fields, and we have a guided brainstorm session to assess potential replication potential for every component, for every LEVIS technology that we have. And if we have a list of all the replication potential case studies, we create a modeling framework and rank them and see which one are actually feasible and which one aren't. And as I said before, the goal is to have from all the feasible components that we could lightweight, so to say, that the whole vehicle could be 25% lighter by doing this replication study. Then the last one, this analysis has just started. So there's not a lot of information on this, but the lightweighting of the vehicle has an impact on the EV motor efficiency, which at the end has an impact on the life cycle assessment. So we consider as input the weight reduction and the results of the replication study. So we also take that already into account. And we use modeling tools to carry out a dynamic analysis of the full vehicle. So how much will it impact the motor efficiency? And by that, also mentioned before, we evaluate the impact on this on the motor efficiency. And we also later on use that into our life cycle assessment, what the actual effect is of the motor efficiency improvements. So this is in short how we at Levi's take on life cycle assessment. If there are any questions, please let me know. Yes, I
Sorry,
think you're
Jose. Yeah, we cannot hear you. Maybe
I'm so sorry. I forgot I was muted. Thank you very much for your presentation. We don't have any questions from the audience at this moment, but I think now we have some time for those that want to stick around with us for a short discussion and maybe some general questions that have popped up during the presentations. I myself was a little bit triggered by several comments also from you, but also from other presenters, including Fatigue for Light, on the issue of, for example, of what happens in future scenarios. We don't have all the information, specifically for, I think, vehicles. We have a lifespan that is particularly long, that's 10 years. Through the circularity that we try to now implement, we are hoping to make that even longer. So the question I would like, if possible, for maybe you can start as well, Floris, by telling us a little bit about how you deal with that uncertainty as to what happens in 10 to 15 years' time when we get back all sorts of materials or other products that maybe by that time will be completely different or maybe even completely out of fashion or just even outlawed.
Yeah, it's a very interesting question and actually something that we are also considering during analysis. And one part of sort of, taking up that uncertainty is what I mentioned before, the sensitivity analysis. So for example, an increased lifespan, we can use parameters to set up a range of what will be the actual effect on the LCA if we increase the lifespan. For other things that it's more difficult because we also, for example, for end-of-life technologies, that increases, that changes a lot over the years. So for example, we have the technologies we have right now for the end-of-life. They're pretty good, as I say so myself. There's a lot of recycling potential, but the thing is it possible on a large scale? And those are questions that we have to ask. What will happen if they're performed on a large scale? Because maybe if we have large batches of components, we use less energy than we are seeing now in our lab by doing these end-of-life processes. And is it actually possible? Because there's also the sort of displacement on where we're designing the current products right now, but the end of life of the vehicles is somewhere 10, 15 years later. So there's also a way, always sort of time. What do you say that? Yeah. It's yeah, the end of life processes are behind on time, so to say, on where you have your design product. So those are problems, and it's really important to have conversations with the industry themselves to get as much information. At the end of the day, it's all a matter of getting the knowledge and getting the information and getting people to talk with each other to set up regulations to set up, exchange knowledge, to work this out, and to get for myself for the LCA to make a prediction, because that's what I have to do, make a prediction, and for them to actually already get ahead with these different processes.
Yes.
I hope that already answers your question. Maybe a long answer, but sorry.
No, that's exactly, I think, what we're here to do, to discuss these issues and maybe, as you say, exchange knowledge between the experts so that they can also have better ideas on how to do things. I think that Christian Leroy might want to jump in on this. He has raised his hand.
Yes, indeed. So thanks for the question. Obviously, for the aluminium industry, there are quite challenges. So currently, let's say almost 200 kilos of aluminium is used in cars, so on average, so it's quite significant. And obviously, with the transition into electric cars, it raised new challenges for us because, okay, the trend is still positive to some extent, because in terms of lightweighting and maximizing or reducing the energy used during the use phase is really important, reducing also the capacity of batteries, so that it's all aspects that plays a good role, let's say, to lightweight the vehicles. But the type of alloys that we use in electric vehicles versus combustion engine vehicles is quite different. So you have the engine blocks, which are typically casting alloys, while in electric vehicles, these are more so-called wrought alloys, which are used. So obviously we have challenges. We are, let's say, looking at this and looking at solutions. But let's say in terms of recycling as usual or as business as usual, it's not any longer the case. So we need to be prepared. We need to look at these changes, which is important for us. And then, with the industry, we are looking for solutions. And this is then obviously important for us to tackle this issue right now, to be prepared for the future. Let's say this is an important point you highlighted, let's say. Yeah.
Thank you for your answer. While we have you, don't go away. I also noticed in the chat that there was an interesting discussion going on critical raw materials and as to aluminium's role in that. I would like, if possible, maybe you can also address that also in a wider sense, because in the end, as you say, electric vehicles require other materials. And how does LCA help us maybe also in balancing those things out between emissions and...
Indeed. Yeah, in the SALEMA project, obviously the focus is on two critical raw materials which are heavily used in the aluminium alloys, which is silicon and magnesium. Silicon is mostly used in casting alloys in quite big quantities. So I think it's almost more or less 50% of the use of silicon is in these aluminium alloys. And magnesium is also quite heavily used in aluminium alloys, maybe not at this level of quantity, but still quite significant. And okay, let's say also aluminium in the recent new list published by the Commission, bauxite appeared as also a critical raw material, but there it was more an issue with the sourcing in Europe, which was mostly from one country, Guinea, and where it's considered as a country with maybe not ideal political stability. So it's why, to some extent, this has been listed as a critical raw material, but there are many other sourcing possible, like Australia, like also Brazil and some other countries in the tropical area. So to some extent was not really linked to availability of scarcity. But in any case, it's clear that we should maximize recycling. This was highlighted. The bottleneck is the scrap availability. So what is available today is what you put on the market 10 years ago or 30 years ago, if we speak about building. So the market is growing, so there is still a need for primary aluminium, definitely. So we need to address both, to reduce decarbonize the primary aluminium production and to maximize the sourcing from recycling. So these are the two main actions we have. And to secure that we can reach these goals of 2050 of the carbon neutrality, let's say, so from the industry. But yeah, I think let's say the scarcity or this critical raw material was an initiative more from the Commission, was not something that we push from the aluminium industry, but let's say this is there, and obviously we look at maybe potential let's say solutions to increase the portfolio of sourcing and securing that the alumina sector in Europe is going well and is with the right sourcing as a material. Let's say this is how we deal with that. Mm-hmm.
Thank you very much for that clarification there. One of the things that I also wanted to ask about in general is I noticed from at least from our own BEVSIM from ALMA, but also the LEVIS approach is to develop a toolkit specifically for designers to be able to better make decisions in the future, because after all, as we have seen, at least from many of those slides that we saw passing today, LCA can be a complex thing, and therefore it's not for everybody to do. And so my question really is, what are the issues or what are our challenges at the moment? Because we can develop these toolkits and we can develop these products like the BEVSIM, but what are our challenges and how do we get that to the actual designers? And maybe Tom, if you're still around, can you maybe jump in on this? As like, what is your take on how we can make sure that designers do actually use this in the future?
Yeah, so that could really be important in my experience. What that was with packaging designers, there are sometimes well, ideas of what will be sustainable, and so they are designing with these ideas in mind. But actually, if you then do an LCA, it might come out differently because you might acquire lightweighting. You think that's the thing to go for, but and of course it's not in this sector of importance. But for instance, if you're going to carbon fibers or other types of very difficult to recycle composites, yeah, you might have that kind of gain in the use phase during the lightweighting, but in the end, because it's not to be recycled, you're losing your materials, and you cannot have a kind of payback in all the impact you put in that. So that's a thing on with these tools, and of course there are also other strategies that, for instance, with a kind of showcases that you inform designers on, hey, this is where we stood originally, and now with applying these kind of designs, we can show that we have a better environmental performance, and of course that's then done with LCAs, for instance.
Yes,
it's important to also to learn their language and understand their way of working, and also try to seek for integration of things like life cycle assessment into their tools. That's also a possibility that you could have an immediate answer on the environmental performance of your new design.
Indeed, I remember a report from LinkedIn that was published, I think, sometime last year about the green skills, which basically showed that there is a discrepancy between the growth of demand for green skills and the availability of those green skills. Not so much because we need more people that are experts in environmental issues, but because we need the actual environmental skills to be more diffusely spread throughout different professions. And I think that that's also where something like the BEVSIM or the IH toolkit developed by LEVIS can help in trying to make sure that our knowledge of environmental issues or our ability to curate those is much better diffused through the, shall we say, the society, but also the corporate world, so that they can actually be used.
Yeah, it already starts at the universities and universities of applied science, that you have in the curriculum, well, environmental knowledge included. And also in companies, one must be aware of these sustainability issues, and within an organization, it's also good that there are really people responsible for the sustainability performance. So, and that's also a way to guarantee that this kind of thinking will be included in the normal processes within a company.
Thank you for that. We have one last question, which I'm not sure who it is aimed at, but I assume it's got to do with the critical raw material discussion. And it's, what about the mono alloy strategy? Is this a possible solution to consider for the automotive industry? I think Christian is raising his hand on that one. Christian?
Yeah, I guess it's referred to aluminium or to steel. It's to reduce to some extent the number of alloys which are used in cars, and to make this car more circular in a way that obviously the less alloy you have, the better you can recycle them and move to a closed loop logic. Obviously, this is a dream. But it's clear that, okay, this is, let's say, maybe an objective for a sector to some extent, but okay, how far we should go to standardization also is a question. But anyway, it's clear that probably today there are too many alloys to be used in cars. So, but obviously this is something which is difficult to change, and OEMs they are the master of that. But I think it's a new paradigm that we are facing to move to more circularity. There is a need for more collaboration along the value chain to really move forwards all together, because they want to keep also their freedom in terms of suppliers and so on. So it's really something we consider at sectoral level that we are starting to be busy with, and see how we can move in this direction. There is not an easy process, but surely it's a good idea to go for more circular value chain. So meaning that, okay, let's go for let's say more restricted number of materials and value and alloys, especially for metals, let's say. But yeah, thanks for the idea. It's then the question.
And thanks for your contribution, Tom.
Yeah, I think indeed what Leroy said, it's especially important, of course, for aluminium, the alloys, but also in steel there are alloys. And if you could reduce that and still have the same functionality, it would be good, especially for recycling. And it also, regarding our other materials, more going to mono materials or easy to separate parts. It will stimulate recycling, and so also by that increase the circularity.
Okay, thank you very much for that final thought. We are run out of time now, so I think what I would like to do now is to thank profusely all of our speakers. Specifically also, I mean, our hosts and organizers from FLAMINGo, Dr. Ioanna Katsavou, thank you very much for all your help in this. I would also think it appropriate to thank the European Commission for their generous funding through the H2020 program, which all of the projects that I've been presenting today have been receiving. And I would also like to inform you that we will, of course, make available the recording that we have today of all of the presentations, so that if you want to look back at anything, then you will have that available. We will also make the presentations available to you for further reference. And of course, we would very much like to invite you that if you have any further questions or you have any further interest in any of the projects or concepts that have been presented today, that you take the opportunity to get in contact with us. We are very happy to set up a more personal approach to the exchanging knowledge. And we really hope to hear from you. So please let us know. And I hope you've had a wonderful and interesting few hours with us today. And we hope to see you at the next one. All right. Thank you very much, everybody.
Yeah, thank you. Thanks for the organization. Excellent.
Thank you. Thank you very much for the organization. Okay. Bye-bye.
Thank you.
Bye,
Bye-bye.
everyone.
Bye.
Bye.
Bye,
Thank
everybody.
you. Have a nice day.
Hey.
Thank you.